In this chapter, we're going to take a look at an introduction to stress and strain and compare what we have found so far to other research findings, and then do a comparative analysis of the empirical measurements that we took and see how that compares to the predictions of Jobst-Brandt and Calvin-Jones. I want to show you part of a very good paper written by Henry Gavin at Duke University, and a graph which is called Measured Spoke Strain Time History During Actual Riding Conditions. But I want to develop this slowly so you don't miss the point while trying to understand a complicated looking graph all at once. The first thing I want to do is define strain, which we will discuss later in more detail in a chapter on spoke elasticity. Going back to our familiar wagon wheel, here it is sitting on the ground, and I'm going to measure the length of that spoke right there, and we'll call the starting length of that spoke unloaded as L0, and L0 is 300 millimeters. Now we have the wheel under a load. The spoke in the load-bearing zone is under compression and will shorten slightly. Now we have this distance here, we'll call that L1, and that is now only 297 millimeters. My strain is defined as L1 minus L0 divided by L0, and when I put in those numbers, I get that. Solving that out, I get minus 0.010, which equals a negative 1%. In other words, what this tells me is that my spoke has shrunk or compressed in its length by 1%. The analogous thing happens with the bicycle wheel. The bicycle spokes are pre-tensioned, and I say analogous because we're inclined to think of the spokes as being compressed as they are with the wagon wheel, and I may say that they are compressed sometimes because that's a simple way of looking at it, but actually they are not under compression, although they get shorter, and I will explain that to you very clearly later on in this chapter. Strain in this graph is actually expressed as microstrain, which is strain times 10 to the 6th, and we see that over here labeling the y-axis, and that is so that we keep the numbers on the y-axis from being very small decimals. It may help you to think of it this way. A microstrain of minus 100 is a reduction in the length of the spoke of 0.010%, 0.02%, and so on. The x-axis is time in seconds and some data about the wheel itself and the rider. We have a weight of bicycle and rider of 930 newtons or 205 pounds. The spoke diameter 1.83 millimeters. The number of spokes is 36, and the rim radius is 309.5 millimeters. With that introduction, we're ready to look at the graph. In the graph, this line here represents zero strain, so anything above this represents a lengthening of the spoke and an increase in tension. Anything below that represents shortening of the spoke and reduction of tension. The data here shows us the average strain, which is a negative number, meaning that the spoke is being compressed as the spoke and the wheel go around multiple revolutions. Now we can see some observations here. The first one is this, that there is a sharp downward spike with each revolution as the spoke goes through the load-bearing zone. So if I pick any given spoke in the wheel, say this one here, it spikes down at that point. One revolution later, it spikes down again, and then so on. Every revolution of the wheel, the tension as it goes through the load-bearing zone goes down. Each time the spoke goes through the load-bearing zone, the negative strain is accompanied by a reduction of the tension on the spoke. A second observation is that there is relative consistency in strain elsewhere. So if we look inside this box, we see that on the left is the representation of the strain on the spoke as it goes through the load-bearing zone. In between that spike and the one next to it, the wheel goes all the way around and returns to the load-bearing zone. This line here represents zero strain, which means that there is very little change in the tension or the length of the spoke between those 2 points. I'm going to expand what's inside the blue box. If you look at the little red spoke in the wheel graphic, we see that when the spoke is pointing straight down, as it is in the graphic, at this point we have a large negative strain, and 360 degrees later we have the same thing again. But those large variances largely disappear between those two extreme points. It took me so long to make this graphic that I want to show it to you again. The fact that the data does not look exactly the same between every two spikes is an indication of the fact that this data was collected during an actual bicycle ride on a less than pristine road where bumps and so on are constantly encountered. Now, it's not particularly important how fast the rider was moving when these tests were taken, but you can calculate it from the graph and the information provided, and it looks to me like about 16.5 miles per hour, which is about 7.4 meters per second. These are the typical crossing patterns that we often see: 2 cross, 3 cross, and 4 cross, and we want to answer this question as a given spoke on any wheel goes through the bottom of the load-bearing zone. What is the effect of the tension on that spoke due to the crossing pattern? We'll illustrate the question by looking at the 3-cross wheel. Here's one aspect of so-called crossing spokes, which is not obvious. This is a wheel, a 32-spoke wheel, in which half of the spokes have been put in, and I want to show you the spokes that are on the drive side as we're looking at it. That's these spokes here. The other spokes are on the non-drive side. They're on the other flange. Our first crossing spoke, which we're going to have green, comes up through this hole here and connects to the rim at that point. As it goes from the hub to the rim, it crosses 3 spokes. It crosses this one, and this one. So this is a 3-cross pattern. The green crossing spoke crosses over this blue one, but under this blue one. It's only at this final crossing where the spokes actually contact each other with force and reinforce each other's tension. Continuing with my same color scheme, this crossing green spoke goes over this blue spoke and under this blue spoke. With a 3 cross, my crossing spoke goes over this one, under this one. With a 4 cross, my green crossing spoke goes over this one, and under this one. The 2 cross gives us over under, the 3 cross over under, the 4 cross over under. In each case, there is only one significant contact point between a green spoke and a blue spoke, so we may expect that in the load-bearing zone there is very little difference between the fluctuation of tension of these 3 situations. This graph, also from Henry Gavin's paper, seems to validate that prediction. As you see in the explanation for this graph, we're looking at the average strain of a right, as in drive side, pulling spoke as it circles the wheel under actual riding conditions. On the y-axis is microstrain, and on the x-axis is the angle from the top of the wheel. So 0 degrees is at the top, 180 degrees at the bottom. Obviously, there is a sharp spike downward in the strain as the spoke goes right through the bottom of the load-bearing zone. And there doesn't seem to be a lot of variance in the graph otherwise, and you're looking at a radially laced wheel as well as one with a 2-cross, a 3-cross, and a 4-cross. Let's do some analysis of my own measurements and findings. One observation, you'll recall that for any of the wheels tested, including this one here, when we add up the total tension of the unloaded wheel and compare it to the total tension on the loaded wheel, we find only a very small variance. Even when taking into account all these variables, starting tension level, the number of spokes, radial or crossing, the number of crossings, the spoke gauge, the rim cross-section, and whether the material is aluminum or carbon, even after considering all of those, we find that the unloaded tension, when we compare it here to the loaded tension, varies only a very small amount from wheel to wheel, and if we add all these up for what it's worth, if anything, we have an average deviation of only about 1.5%. And I believe the primary cause of even that small error is the inaccuracy of accurate conversions from the meter to newtons of force using the conversion tables and the interpolation required. We can draw two conclusions. One is that the tension in the loaded wheel is redistributed from the unloaded wheel, and two, the total tension of the unloaded wheel is equal to the total tension of the loaded wheel. We can do some good comparisons here because we only have one variable. They're all made of the DV, 24 holes, radial lacing, the same starting tension. The only variable is really the diameter of the middle section of the spoke. Another observation is this: when we looked at our low spoke tension wheels with an unloaded tension of about 784 newtons, and then we compared wheel 1, 2, and 3, the only difference between them was in the spokes that were used, and we found these graphs and a decrease going from left to right of tension in the load-bearing zone from 53% loss of tension to 49 to 35. So once again, I think we can draw from this a couple of conclusions. One is that the fluctuation of tension in the load-bearing zone for the leader spoke is greater than the race, which is greater than the laser. And number two, the fluctuation of the tension in a butted spoke is less than the fluctuation of the tension in a straight gauge spoke. And we can graphically depict this. On the x-axis, we have degrees of rotation, and you're looking at a repetition 6 times of the data. On the y-axis is the force in newtons, and here we see the 53% reduction in the tension as the spoke goes through the load-bearing zone. This is the same graph for the race spoke, and the thin middle section laser spoke showing the smallest percentage change. And here are all three plotted on the same graph. Wheels 4, 5, and 6 have a starting tension of 1,274 newtons. Now, when we look at the high tension wheels with an unloaded tension of about 1,274 newtons, once again, wheels 4, 5, and 6 are exactly the same except for the different spokes used. Same tension in every case. And we saw the results. A 22% decrease in tension going through the load-bearing zone here, 19% there, and about 19% here. So we have essentially the same conclusions. The fluctuation in the tension in the load-bearing zone of the leader is greater than the race, which is about equal to the laser. And again, the fluctuation of the butted spokes tension is less than straight gauge, but only slightly less. Here's our graph of the high tension wheel using the straight gauge leader spoke, the double butted race spoke, and the double butted laser spoke, and all three laid on top of each other. We can also show the high tension and low tension graphs on the same chart for the Supreme leader spoke. the Supreme race spoke, and the Supreme laser spoke. And these are the combined graphs of the first 6 wheels that were tested. And then when we compare the low tension wheels with the high tension wheels going from left to right with the leader spoke, the straight gauge spoke, we had a change in fluctuation from low tension of a 53% decrease to a 22% decrease at high tension, with race 49% compared to 19%, with laser 35% compared to 19%. And this appears to agree nicely with the statements made by Calvin Jones of the Park Tool Company, and I'll quote that again for you. As the wheels rotate while you ride, the spokes that are at the bottom next to the ground will momentarily become lower in tension, then regain tension as they rotate past this low point. Wheels with a relatively low overall spoke tension actually see a greater swing in tension as compared to wheels with a greater overall tension. And that's the end of the quote, and we clearly have seen that play out. However, none of these results agree with some of the statements made by Jobst Brandt, as particularly that only tension changes occur in the spokes at the bottom and there are no changes in tension elsewhere. That certainly does not agree with any of the data that I have collected. It is, of course, true that stress and tension changes are the greatest at the bottom of the wheel. Let's compare 2 other wheels. We'll start with wheel 5, which is a velocity deep V rim, 24 holes, radial lacing, race spokes, and nice high tension, and we'll compare that to wheel 7, which is exactly the same except we have a 2-cross pattern on both sides. When we compare these 2 loaded wheels, starting with the one on the left, and we look at a given spoke as it rotates through the load-bearing zone, starting at here, it has gone up 10%, down here, -3, it loses 19% here, back up a little bit there, and increasing to 7 here. With wheel 7, with a crossing pattern, we have a very similar result. Starting out, it's gone up 12%, down here -3%, -14%, same tension here, 0% change, and +7. So we have the only significant difference really is a small change in the fluctuation at the bottom of the load-bearing zone from a -19% to a -14% with a crossing pattern. Perhaps we can explain this as follows. We'll highlight, in the case of the radial wheel here, the spoke that is straight down at the bottom of the load-bearing zone. In my crossing wheel, this one is at the bottom of the load-bearing zone as well, and I might expect that I will get some help in the tension reduction from this forcible crossing with the crossing spoke, where the crossing is at this point. However, the problem is that my crossing spoke is already rapidly losing tension as it itself gets near the load-bearing zone, so that the change in the tension of the green spoke is not reduced very much. And that allows us to make this conclusion that compared to radial lacing, a crossing pattern reduces tension fluctuations slightly at the bottom of the load-bearing zone. Now we're going to go back to these 3 graphics that you've seen before and make some additional observations. Let's take this discussion one step farther. This is a 36-spoke wheel, and we're looking at 18 spokes on the drive side. All 3 of these are the same except for the crossing pattern. This one has a 2-cross, this one a 3-cross, this one a 4-cross, and we ask, is there any benefit to going with additional crossings? Here you can see highlighted in blue for each wheel the 9 pushing spokes, and we're going to show in red for each wheel 1 crossing spoke. If we look at all 3 of these, we have a blue spoke at 180 degrees, a red at 160. a blue at 180, a red at 160, a blue at 180, and a red at 160. So I have exactly the same picture with all three wheels, and I have one forcible crossing of the same two spokes at the same point. Now, if I color my hubs here in orange and put in a line here which represents a line tangent to the hub, and that is also a line which is the base of those three little isosceles triangles, which I can expand like this. You see that other than a small difference in the height of the triangle to the apex, all three of those pictures look exactly the same. That gives us a pretty in-depth understanding of the behavior as seen in this graph of the tension and strain as the spokes go through the bottom of the load-bearing zone. We see a virtually identical curve for the 2-cross, 3-cross, and 4-cross. Which brings us to this conclusion that there is no noticeable difference in spoke tension changes between wheels with 2-cross, 3-cross, or 4-cross patterns. There is a slight difference in the length of the spoke and where the spoke attaches to the hub. With the 2-cross, the elbow is located at the 7 o'clock position, with the 3-cross about the 8 o'clock position, and with the 4-cross about the 9 o'clock position. Even though these wheels all act the same and what we have been discussing with respect to spoke tension, they are obviously different, and they are quite different when it comes to torque transfer, a topic that we will discuss exhaustively later on. Wheel 7 is a deep V, 24 holes, 2-cross on both sides, race spokes, and nice high tension. And we'll compare that to wheel 8, the only difference being that wheel 8 has a velocity fusion rim instead of a deep V. For comparison, here are the cross sections of the deep V and the fusion. When subjected to vertical load, if we do a comparison of the percentage changes in the tension, we see that they look pretty similar. There's maybe a little bit more of a loss of tension, slightly more in wheel 8 with the fusion rim than was the case with the deep V. Now we're going to do a comparison of wheels 9, 10, and 11. Wheel 9, a deep V, 32 holes, 3-cross on both sides, race spokes, and nice high tension. Wheel 10, everything is the same except with a velocity fusion rim. With wheel 11, everything is still exactly the same except that we're using a carbon composite rim from Knox Composites. And this is the loaded data for all three wheels shown side by side for ease of comparison. I think that the pattern seen here in all three graphs is substantially the same, so that there would not appear to be any difference in the behavior of the spoke tension in any of these three wheels.